I hope you all can hear me now. Okay, so let me get started. So, howdy, my name is Jian Tong. I already introduced myself early in the morning, just in case some of you joined us a bit late. I'm an assistant professor from the Department of Visualization, and I'm also an assistant director at the Institute of Data Science at Texas A&M. So this is a work I've been leading 1.5 years ago. It's more or less like a secret project. Not what I say secret means it's something it's working. We are working on it, but didn't publicize it in the last 1.5 years. So it started as an educational project. What we are trying to do is to build a digital twin. The goal was to build a digital twin for the Redis campus. But we started as a project to build up virtual environment for us to run our cars in it. That was a request from Dr. Des Song from Computer Science Department. He was leading this he was leading this auto drive challenge team to compete at the international event. And during the pandemic, his team couldn't touch the car because the whole campus was locked down, and he's really interested in getting something running. So after I talked with him, I said, okay, why not? We just start doing something like this. We build up some virtual environment, and we can get our students started running something virtually without them waiting for the all the restrictions removed for them to get their hands dirty with the cars. So that's how we got started. So the ultimate goal of this project is to provide a research platform to develop and test autonomous vehicle technologies. And also we want to use this platform as a collaborative environment for multidisciplinary education. And finally, after some discussion with the folks from the Redis campus, like Brian Hoover and others, when they told me about what's going on with the 5G testbed, it seemed to be a wonderful opportunity to work with them to see how we can leverage their 5G testbed to do something more interesting. As I mentioned, this is starting as an Angular challenge project. And for those of you who are not familiar with this project, it's one of the best things, this college of engineering is offering to undergrad students. So this organized in form of research projects, in form of special topic course. And faculty members from the college of engineering can propose research topics, and the students senior, actually some of the students I had in my classes are freshmen. So as long as you are in engineering, you can register for the course. As long as the faculty member is okay, you can pick up to 4 credits to take this course and start doing research, real research. So we started this in for 2020, and then the last group of students, I think they finished the project in 2021 because of the time constraints. I couldn't pick it up this semester, but hopefully we can continue with this project in the future. This project is closely linked to the auto drive challenge project that I just mentioned that Des Song is leading. As there are many other faculty members supervising this team, including myself. And my team mostly organized in forms of Angular challenge team, which is contributing mostly to the virtual environment. But unfortunately, it's not used for the real challenge, for the auto drive challenge, but a lot of students we trained for this for the Angular challenge project, they now work with Dr. Song in this auto drive challenge competition. So this team got first place, which is really amazing, considering all the difficulties the team has been facing in the overall dynamic events in the first auto driving challenge, which was ending in summer 2021, just last summer. And the team was also selected to compete for the second round of auto drive challenge competition, starting for last year. So the team now has 2 cars. One is the older one, which is from previous competition, and then there will be a new one from donated by GM with all the sensors, all other stuff coming with the car. The total price about close to 100K for a car like this, close to including all the cost, etc. So after I joined the Department of Visualization, I started thinking about some research directions, based on my own background, mostly on physics and simulations and modeling. And digital twin and also all the simulation related modeling work seems to be the right direction for me to do. And I started thinking about the project roadmap based on the educational project we started 1.5 years ago. So this is more or less like a roadmap, I think, for this project. I think it's also give us a good understanding about what we have been doing and what we are going to do. So we started with a virtual map, which is just a simple road network of the Redis campus. So we took the HD map from the Redis management team. Some of the folks, I believe, the first HD map I got it from Jim Wall. He retired last October. I believe last October he retired. But his team has been working with us to get some help on their end for us to work on things that might not be easily accessible by other teams. So their help is essential to get us started. We got some help from them to get HD map, and we generated road networks based on the HD map using the package called the Roadrunner, which is a software product by MathWorks. And on top of the virtual map, we started building the 3D environment. 3D in a sense is not just the 2D map with all the road and road networks, which are all confined where your cars can go and your walkers can walk. It also have the 3D building structures, and you can have a photorealistic environment. And then the last, which is not the last, it's the third one. The third milestone that we have been targeting is the autopilot system, actually still under development, but we have some prototypes which is already working well in a simulated environment. We are trying to add more perception modules, and I'll talk a bit more about that today. So we start with the virtual map. The package I just mentioned called the Roadrunner. It's a very, very nice tool. Back then, I believe the package was called Vector Zero. It was acquired by MathWorks, I believe, right before we started working on this. And MathWorks, they gave us free access to Roadrunner as a part of the agreement with Autodrive Challenge organizers. But after we talked with the MathWorks representative here on campus, they told us that Roadrunner is accessible by everyone here on campus. Actually, it's engineering, I believe, because we paid the license, and the license covers Roadrunner, including MATLAB, etc. And the beauty about this Roadrunner is that you can use that to generate this open drive road networks, which is a standard that could be recognized by not only the simulator we are using, but also many other simulators on the market. So on top of the virtual map, we start building up 3D structures, and the students started using Unreal engines directly. Actually, in the color environment, which I will talk about in the next couple of slides, there are also other simple modules for you to create your own 3D structures and build up towns and cities like that, which will be much better than simple geometrical objects. And with Unreal Engine, there are many other extra things I can directly do based on Unreal Engine without getting into the simulator. You can do exactly what Andrew showed in the morning, that you can do simulations, you can run stuff, you can do the controlling, you can connect your streaming data, you can do a lot of things like that. But what we are doing here with the color that I'll be showing next is based on Unreal Engine, this gaming environment, but it has an interface for you to write programs that are tied directly to autonomous vehicles and self-driving cars. So Color is an open source simulator, which is one of the major reasons why we picked Color. I talked with NVIDIA folks, and we even invited some people from NVIDIA who are doing this drive scene, which is a NVIDIA package for autonomous vehicles. The problem is back then when we were talking with them, it's not freely available. Even if you buy their DJX system, big 200,000, 300,000 system, if you want to buy those, they will give this software for you for free to use if you're working on related projects. But for us, we didn't have the budget, so we started looking into some open source alternatives. So I talked with Sarah, three clients, Sarah Pali. He suggested that we use a Kala, and that's what we use. And Kala provides this API for you to start your. Kala it's more or less follows this server client server model. So you have a server running in the background with all the maps, everything renders going up, more or less like a game server running remotely. And every client, every user, or every user of this system could log in or could connect to the server as a client. So you can log in as a client to change the dynamic weather condition. I can log in to do my driving. So everyone is more or less like an individual player in a game environment. So underneath, Kala is using Unreal Engine itself, so which makes makes the transition from the Unreal Engine development done by the previous team easily to Kala environment, because they are using Unreal Engine in the backend anyway. And that gives us a very good starting point for students to start doing something for real in autonomous vehicles and doing some autopiloting system study. So we do have a couple of students, some senior computer science students who joined this Engage Challenge project. They started a reinforcement learning training based on the Kala environment. So they generate segmented plots like the one showing at left bottom here. So with that, you can do quick training with data generated from the virtual environment without you collecting the data yourself, going outside with cameras and doing your segmentation yourself. So all this are done automatically, because you can have very nice segmentation of the trees and the structures, because you already know, because we know it's trees, it's a road, it's a building. So you don't need to do the error-prone segmentation either by hand or automatically through some programs. So that's the beauty about this environment. So your data is pretty clean for you to train. But of course, some people might say the errors are the things we needed to recognize in the real life for you to train a realistic model. But that's something else we discuss later on. But as far as the simulator itself goes, a clean data set will get you started very, very quickly. Your cars should be able to recognize all the structures and make decisions based on whatever it's detecting. So the right bottom figure here shows the LiDAR sensor that you can actually have multiple sensors installed in your car. These sensors are virtual sensors. You can put it anywhere on top of your car, at the bottom of your car, anywhere in your car. It will detect all the surrounding environment based on the some algorithm and give you all the point cloud connection without you installing any physical facilities. So that's the beauty about this virtual environment. So this is one simple example that we are showing a real car, high fidelity car model running on the Raleigh campus. Oh, I'm sorry. I'm not sure if you can see. It will take a while. It's kind of empty, but that's what Raleigh campus was. It's not like it was. It's like that. In many places, it's almost empty. So we didn't put a lot of buildings, but the road networks are already laid out properly. So we are following the map at Raleigh campus, laid out the road networks, and we put some buildings surrounding, based on the Google map we have, based on some field pictures we took. So it's going along the road, and the road is here. The already laid the sides, the left and right, and all the constraints were posted based on the real size of the image we took. So sometimes they might be very narrow, some are very wide, but more or less they're very close to what you're seeing in real world. I'm not sure which building this one is, but they just took one building and make it look. They took one asset from Unreal and make it embedded into the system. So we didn't spend much time going into the detail to make everything photorealistic. But in the longer term, I think we can do that. It's not very difficult at this point. So and another one of the future directions we are currently targeting is the so-called auditory perception. So unlike the visual perception that everyone is doing nowadays, with not only the cameras, lidar sensor, and also radar sensor. Radar is more or less like video, but it's not optical range. Even sonar, you are detecting using different ways of detecting different signals, but the auditory information is not widely used in this scenario. So one of the beauties of this environment is that we can integrate different perception systems easily without spending a lot of effort to get the physical system set up, even though in the longer term or near future, we are looking forward to get some physical sensors installed and getting some field tests done. So what we are trying now is to put virtual verifier attached to each ambulance or each fire truck and each police car based on what type they are. We attach a certain audio files to it. So this file together with a car will be treated as an object inside our environment. So we have a sensor, virtual sensor, detecting all the sound. So we're not directly taking the file, we are detecting the sound sent by this object when it's moving around this environment. And then based on the information we're detecting, we use that to make a judgment to see if it's a police car or a fire truck or it's ambulance. And we also consider the attenuation of the magnitude. So when the fire truck is farther away, you can hear the sound is lower, and when you're getting closer, it's getting bigger. And we also consider Doppler effects. It's programmed into the simulator, and the student from visualization department currently is working on this. I'm sure you are very, I'm not sure if you all can hear the sound. Let me just lower the volume. So this attenuation of the magnitude, it's simulated, it's inside. So based on one of R square rule, in this world you can define your own physics. So 1 over R squared is what we use, but we can change it if we want. So this is a diagram. Even though it looks very simple from what I'm showing here, but actually it's a very complicated system, and you need to consider both the physical input, streaming of the data. You want to consider the simulator itself. You want to consider the perception side. You want to consider the simulation side. And so this is a part of the ongoing work, and the student currently working on a paper on this. So I don't think it's a good idea for me to show it here, but I think it should be fine because the learning curve is not that it's not that shallow for everyone to pick up this quickly. But I think it's a good idea for you all to see how much effort the student put into all this system. So I'd like to thank Nina Kang, an undergrad student here and computer science and math, and also Lisa Cassidy from visualization department. And they both are undergrad students, which are really amazing, and how good students we have here at NM. And also this project has been made possible by many students in the Angie Channing project in the last 1.5 years. So with that, I want to conclude my talk. And any questions? Okay, here I am.
A great talk. Very interesting. Thank you very much. I have a question about using the VR system. Normally we would use the VR system to train like a human driver. But in your case, it's autonomous vehicle driving. So I'm wondering, like the application of this VR for enhancing the autonomous driving, like in which aspect it will enhance it. For example, whether you do need the real-time VR or simulation. Otherwise, maybe offline simulation can actually tell whether the autonomous driving algorithm is correct, is reasonable or not. If there are any, let's say, mistakes made by the autonomous vehicles without the actual real-time, which is normally slowed down than otherwise speeded up simulations.
Yes, actually, what I distribute here is based on Unreal Engine's gaming system, and just consider the autopilot system itself is just controlling the car itself. So it could be turned off and turned on quickly, easily, and you can have AR built into. You have all the gadgets. I bought two Quest 2 recently and gave to each one of them as a bonus for them to play with it. And they are trying to explore different scenarios. So you can just put a block in front of a car and let's see what the car will do. And all this kind of corner cases could be done easily with this virtual environment. And developing AR VR application based on Unreal 3D environment like this, it's almost trivial in the sense that it's built into them. It's just like how you want to put your camera and put your controlling body inside this environment. But as long as the environment itself is ready, and the rest will be mostly, it's more about creativity. So what we are doing here is most like building up the framework for all these future students to just get inside and play with it. Let's see what will happen. And on the research side, as I mentioned, we are mostly targeting some corner cases. For example, what if you put a big mirror in front of your car? What will happen? So what if someone's shooting? If your car, hears sound of bullets and sounds of gunshots, what will you do? And those kind of things, could be done, but it's much easier to do it in this virtual environment to see, how you can deal with those kind of scenarios. I think that's kind of like interesting cases for us to look into with this system.
I see. So the applications are still for the human users to look inside the VR system, to look at the simulations and or the reconstruction of the built environment affecting the autonomous driving. And in the meantime, probably the algorithm can be tested, like autonomous driving algorithm can be tested by simulation offline or integrated together with the VR system.
Yes, I think what you're saying is exactly right. I think on one side, we can test the environment, how you can interact with AR, VR technologies and play with the environment. And on the other end, we use whatever environment you have here. This could be dynamic environment. We can train in our system, use reinforcement learning or some other methods, or just controlling theory without worrying too much about learning things continuously. We just use our decision trees to decide what we need to do based on the scenario.
That's great. Thank you.
Thank you.